So, good evening, ladies and gentlemen. My name is Dmytro Tvardovskyi, and today I will tell you about my recent research of eclipsing binary stars of O-C curves and application of software MAVKA. So let's start with binary systems, which are 60 to 70% of all stars on the sky. So there are a lot of stars to observe, to study, and some of these stars are eclipsing binaries, which can be observed from Earth. And we usually study these brightness changes. Also, there are not only brightness, but also period changes in such stars. In some cases, stars in binary system are so close that the mass transfer begins due to relatively close position of the components in the system. And in addition, sometimes third or even fourth component are present in the system. That could be a planet, an exoplanet, or a small star. We made our observations in Slovakia in 2017. We observed several minima of V0523 Cassiopeia, and this data was used to make our research, but most of the data was taken from AVSO International Database. Usually from a light curve, we consider only minima, and usually this is primary minima because almost all observers observe only prime minima. And sometimes the moment of this minimum is shifted from its calculated value. This shift we call O-C. And now I'm going to talk about software MAVKA and how we get this difference. So software MAVKA is the program created by Ivan Andronov and Katerina Andrich. This program is application of 9 various methods. These methods could be used for approximation of symmetric and asymmetric extrema, both maxima and minima. So this program is quite universal. In addition, it can choose the best method for each unique extremum, but we decided that it is necessary to decide which methods are best for current type of extrema. In addition, you can save the results. The results are moment of minimum and magnitude of minimum with their errors, of course. So there are 9 methods realized in MAVKA: 3 for symmetric extrema, 3 for asymmetric, 3 for exoplanet transits. All of them are tested. What tested? I mean, we created some synthetic data, then we run our algorithms for this data, choose the best methods, then apply it onto real observations. There are some functions which we used as synthetic data. This is the plots of these formulas. And we changed the parameters such as noise, number of points, and also we cut 1 or 2 branches of extremum. This is the synthetic data set. There are 4 parts, so with different amount of noise, points, and symmetry of interval. There are synthetic extrema and the table with results. So in order not to consider such huge table, we computed some of the logarithms and created such table. So if the method is green, it is applicable for current shape. If it is yellow, it's okay, but better not to use it. And if it is red, it's definitely a bad method. So for asymmetric extrema, the best method is polynomial. For symmetric, either symmetric polynomial, either parabolic spline or asymptotic parabola. Totally, we computed over 1,000 extema. 1,168 of them are already published in February of this year for 31 stars. This is the published results, already published. And there are a list of articles where software MAVKA was applied. Let's return to Almanisy curve, to main topic of our research. If we get large enough set of the Almanisy values, we can create a plot, and according to the shape of this plot, we can make a decision what happened with this star. The perfect case is horizontal line, but we never observe it. It means that period and the initial epoch are absolutely correct, and nothing is changing. Inclined line means that there is an error in period value. Parabola means that period either increase or decrease. Cyclic variations means that period change cyclically. Also, it could be cyclic and linear, or cyclic and parabolic combination. Parabolic trend or parabolic shape of Almanisy curve means that there is a mass transfer in the system. And we computed the rate of the mass transfer and, of course, the error, if possible. To compute the mass of the third component, which could be explanation for cyclic Almanisy curve, we need to solve the problem of three bodies. It could be solved only numerically, so we simplified it. We considered two close bodies of the system as one, and the third component as rotating around this one big star. So we just use the simple Kepler's equation, third Kepler's law, and some other formulas to create this formula for calculation of the mass of third component and its error, of course. So to compute mass of the third component, we need to calculate it several times, putting the first value, for example, 0. Then it will be more and more accurate with each next iteration. Finally, we detected that some stars have asymmetric Almanisy curve. We explained it as a possible elliptical orbit of the third component and computed 6 main parameters of this orbit: the size, the measure axis, eccentricity, 3 angles of inclination, and period of rotation. This is the formula for description of Almanisy curve. In addition, we considered weights, so visual and visual data was considered as weight 1, photometric as much more accurate, we considered as weight 10. And finally, we created a software in Python to not solve all the stuff numerically. I mean, not numerically, but by hand. So we solved it numerically in this program. There are possible shapes of the Almanisy curve in the model for the case of circular orbit. Also, there is parabolic trend with some changing of parameters. And finally, for elliptical orbit, the shape of Almanisy curve could be almost anyone, especially for large eccentricities. There is an example of observations versus fit. So our model is quietly good for fitting the observations of such stars. And the deviations improve that. Any kind of deviations. So if we evaluate 2 parameters and calculate the sum of deviations, all our results will be in the violet region on these plots. Also, there is an example of final results. M with dot is rate of the mass transfer, M3 is mass of the third component, and for all 31 stars, as we computed, the mass of this component means that it is a star. It could be something like not a normal star, but brown dwarf, but it's not a planet, definitely, within the errors. So that's all for my report today. Thank you for your attention and maybe some questions.